Okay, so J.J. Thompson had basically done this experiment with the cathode ray tube. I'll show you what it looks like. Okay, so if you take a look here, this is the cathode ray tube, right? And so the idea is that you have your cathode here, you have your anode here, and then you're going to put a high voltage through here. So this is going to produce a cathode ray, and then this ray is going to go through this magnet. Now, this here basically shows that you were able to sit there and move in this context your negative charge. Your negative charge is going to go towards the positive because opposites are going to attract, so it's going to be deflected that way, right? And so the negative is also, if you have a negative and negative, right, charge, what happens when you bring two negative charges together? They're going to repel. That's right. They're going to repel. They're going to repel from each other. Okay, so we know that opposites attract, right? Kind of like relationships, right? Okay. So then Milken came along and he did oil drop experiments, right? And so this is pretty cool, right? So what he did, he got this oil and then he charged the oil, right? Or oil particles. So they were electronically charged. And then he put in his little device here. You have a positive, you have a negative, right? And then the oil was actually sprayed onto the screen and then dropped through the hole. And then if you put the electrical charge on it, then you could actually have the oil going in the opposite direction, right? Or sustaining, remaining suspended. Yes. How do you? So the ways that you can do it is that you can make chemical modification to give it a negative charge. So like say you have oil and then you put a chloride in it. That will give it a charge. Or you put an oxygen. Right? And you'll see this a lot in biology, right? And also ozone. So and when we say, well, all it is those long fatty acid chains, right? And then you just have some charge particle. Okay, so he did the experiment, and then he did the math. He actually got the mass of an electron. And so the mass of an electron is 1.107 times 10 to the minus 4, 10 to the minus 31 kilograms. Okay, and the charge on an electron is going to be 1.6 times 10 to the negative 13 coulombs. That's the units that we use for charges. Okay, so Thompson basically said, okay, so we have these positive and these negative charges. And these positive and negative charges, they're like in this bread pudding or like in a cookie, right? Chocolate chip cookie, where you have your positive and your negative and your positive and negative throughout the entire thing, right? So that's what Thompson believed. Now, what is it? Naguaka, also a scientist around the same period, Japanese scientist, and he says, no, I believe that the charges are orbiting, kind of like Saturn does. Saturn has rings that orbits it, and so the positive is on the inside, and then the negative is on the outside. Okay. So these were the two models that were kind of competing in that time period. And so there's a couple of people said, well, maybe that's the case, but we don't know, stuff like that. So they did the Rutherford experiment. So they took this piece of gold foil. Now, and then they shot it with alpha particles. Alpha particles are positively charged particles. Talk more about alpha particles when we get to chemistry, just a bit more to what they have. But alpha particles were shot into the gold foil, and then they noticed you had deflection. And then you have some that were able to go straight through, right? And so again, if you have a positive and a positive that come together, what's going to happen? It's going to repel. So then you're going to deflect, right? So then you're going to get deflection, and this deflection is organized, right? It's not just random. They noticed that it wasn't a random event. It was pretty organized when they saw the deflection. So that meant that it wasn't just dispersed positive charge throughout this molecule or this atom, right? It's just that the positive charge were all kind of neutralized together. central isotope. Okay, and so, and then if it was negative, it was able to shoot straight through, and then you would get your alpha particles at the end of it. So you got a combination of both, right? So that meant that there was some organization that was to it. So they kind of looked at it and they said, well, let's design our hypothesis based upon this data, right? So again, positive being the center of the atom, it would cause deflection. Where if the negative was on the outside, it would just kind of push it through, right? And so it would just kind of float on through, okay? So that meant a couple of things, right? One thing is that you had this really, really small center that was positive, right? And then you had this big old cloud that was negative, but it wasn't like overwhelmingly negative, right? Because your alpha particles were able to still continue through, okay? So this led us to the model that was more towards the Japanese scientist. Okay, I butchered his name. I have to pronounce it. So, anyway, it led to this model being closer to what we're expecting. The only thing is that different is that now we know that the nucleus, right, which is composed of the positive charges, and then the electrons, which is the negative charges. The nucleus is in the center, and then the electrons are on the outside, and they form what we call a density cloud. Right? And so it's just like a cloud of negative charges that's circling the nucleus. Okay, I'll show you a figure of that later on. Okay, so next thing I want to talk about is isotopes. Isotopes are, the basic definition is it's the same atom but a different mass. Okay, same atom but a different mass. So for instance, we have carbon-12, right? Okay, so when we write the nuclear symbol for a compound, it's written top number here represents mass number. The bottom number here represents the atomic number. And then if you have a number here and a charge, this represents the charge. Okay. And nobody wants to talk to me until I get into class, and everybody wants to follow. Nobody loves me otherwise. Okay, so mass number. Mass number is often associated with the mass of that atom. Now, since we have what we call an isotope, isotope meaning what again? Same atom, different mass, okay? So, the isotope, one of the isotopes of carbon-12 is carbon-13. Okay, so carbon-13 weighs 13, carbon-12 weighs 12. Okay, you guys with me so far?
Yeah.
Can you do me a favor? Can you look on your periodic table? Check your periodic table, Daniel. Dude, that's the example. He knows. Okay, on your periodic table, we have what we call the atomic mass or the atomic weight. Can you guys find it for carbon? Say it loud. 12.011. Okay, so let me explain to you how we got this one. Okay. So what they did, they went out, they collected all of the hydrogen. I mean, all the hydrogen, all of the carbon, right? From nature. So they collected a little bit of carbon from nature. And then they went through, and then they determined what was the weight of that carbon. They used an instrument called the mass spec. Mass spec allows us to sit there and separate an atom based upon its mass and based upon the charge. So we kind of set it up, we kind of charge it, and then we'll run it through this machine to get the mass of that atom, right? So they got two masses, right? One that weighed 12 and one that weighed 11. The one that weighed 12 is about 99.89% of the carbon that was found. The one that weighed 13, sorry, not 12 and 11, 12 and 13, the one that weighed 13 was 0.11% of what was found. And so they sit there and said, well, one weighs 12 and one weighs 13. So then they multiplied the 12, you guys can do this just to check it out, just to be sure. That weight of 12 times the decimal form of the percentage, what would that be? Okay. Okay. Somebody do that heavy lifting for me? Well, point what?
0, 0, 1.
0, 0 or 0, 1?
0, 0.
And then on the periodic table it says 12.0, 0. Okay, so I'm off by something. This should 12.011. So my percentages might be off by 8%. So it might be. Right, it is 8, 9, 1 here. Right. I have to look it up to be sure. I'm rusty. What do you end up with? If this was 8 point. I used to know it's like that actually. I think I carried away with my service. He knows, right? Do me a favor. Can you do the 13.11? Yeah. So point 0.01. 12.018. That's if I put 0.11, right? So it was. If I put 0, 0. So that gives us 12.011, right? Oh, you're saying if I use this 89 point. Okay, so let's use the 89 point. It did work out, yeah. 89.89. Right, it's at 0.9989. Because that's going to give us a 12, right? 12.0011. Too many zeros.
Yeah.
That's what I'm saying. This is then my math wrong here. So this is 999. Yeah. Sorry, I'm obsessing. Okay, well. I'll do the calculations later, but ultimately, what was supposed to happen was we should have added up to this number exactly. For some reason, we're off by a whole zero here. There's a whole, and I'll have the calculation later. But the moral of the story is that you're supposed to be able to add it up, and it should add up to the value that we have, right? And so on your periodic table, because that is the abundance that was observed in nature. I will have to recalculate the numbers and do it again. It's weird to me that it ends up adding up to 12.0011 instead of 12.011. But anyway, I'll have to redo the math. Okay. So, in other words, so if we had 100 carbon atoms, right? 98, 99 of the 99.89 of them are going to be that carbon 12. So that means that the majority of them are going to be carbon 12, and you're going to end up with one that isn't eventually. Okay? So you guys have heard of carbon dating, right?
Yes.
Okay, what is carbon dating?
It's when so carbon 13, they use it to date how old, roughly how old.
Yeah, how old? So I use him as an example, remember? Yeah. Yeah, so we know that carbon dating isn't carbon calling everybody up and saying, hey, baby, what's your number, right? We know it's actually using the isotope, carbon 13, and finding out how much carbon 13 you have and using that to determine how old something is, right? Okay? So these are examples of isotopes. Now, the difference between isotopes are the weight. The atomic number represents, what does the atomic number represent again? Talk about that. It defines the atom, but it represents the number of protons. Okay, so the atomic number represents the number of protons. On your periodic table, your atomic number is listed at the very top of the periodic table, right? So for instance, hydrogen has an atomic number of what? Hydrogen.
Oh, 1.
1. Carbon has an atomic number of 6. Okay, so that means that carbon has 6 protons. Protons are positively charged. Okay, now the thing that you need to know about atoms, all atoms on the periodic table are neutrally charged. What do I mean by that?
They have the same amount of electrons as protons?
They have the same number of electrons as protons. They're not. We'll talk about it in a minute. Okay, so you said that carbon has 6 protons. How many electrons must carbon have?
6.
And electrons are negatively charged. Now, there is a third subatomic particle called the neutron. And the way that we determine the number of neutrons is we take the mass number and we subtract that by
Protons?
the number of protons. So in other words, your mass is going to be made up of protons and neutrons. Okay, so in other words, your mass is going to be made up of protons and neutrons. Okay, so then how many neutrons does carbon have? 6 for carbon 12. How many do we have for carbon 13?
7.
Okay, how many protons? 6. How many electrons? 6. Okay, so carbon 13 has 6 protons, 6 electrons, and 7 neutrons. Well, carbon 12 has 6 protons, 6 electrons, and 6 neutrons. So does that make sense? Okay, so somebody has to ask. Who's going to ask me? What is the question? The next question you should be asking as a scientist. Anyway. What was that? Ions? Well, we'll get to ions, I promise you. That's a good question. Shady. It's going to be. Dang. What is the next question? How do we calculate the charge of an ion? So that's the biggest question. Those are 2 good questions. Good questions. Good. Okay. We'll get there, I promise. There should be one more question that you guys are thinking about.
Where does the weight of the electrons go?
There we go. Where does the weight of the electrons go? What happened with those electrons, right? Because you're taking into account, aren't there electrons there?
Yeah.
Right? Okay, so let me explain to you. So I weigh 220 pounds, right? If I put a speck of dust on my shoulder, how much would I weigh? I would still weigh 220 pounds because that speck of dust isn't going to make a difference in my weight, right? So electrons are so light that they're like a speck of dust, right? So we don't take them into account for the weight. So they're like 5,000 times less in weight than one proton, right? So they take 5,000 to actually make a point, right? You guys are good? You guys are tired. You ate too much? It's a Monday.
I did actually.
You ate too much. Yeah, that's what it was. You had too much time. You know, you guys are out there. You had a chance to digest your food a little bit. Now you're getting a little tired. Guys, tired. Okay, so we know that the electrons are going to weigh so little that they're not going to count towards the weight. So we don't count them towards the weight. So the weight is only the protons and the neutrons, and that's it. And the protons and neutrons are going to be found in the nucleus. Imagine that. Okay. So questions? Yeah. So the electron's mass doesn't count because it's too small. Exactly. Okay. Okay, so let's see if you guys have a good understanding. So let's say we have this element, or this atom. Okay, tell me the number of protons, tell me the number of electrons, and tell me the number of neutrons.
Wouldn't it be 184?
Because this is the isotope for tungsten 185. But we will talk about how you can use your periodic table to give you that ballpark figure. Okay, so number of protons. 74. Number of electrons. 74. Number of neutrons. And how did you get 111? Job. Everybody else does that? You have a question, I see it in your face. Don't lie. I want to ask it.
So for the protons and electrons, it's just the atomic number.
Yeah, so for protons and electrons, it's going to be the atomic number. Yes,
And neutrons by or minus the mass of the
that's right. Yep. Okay, pretty simple. Not too hard. Okay, now what charge does it have on it? What was it? It's neutral, so it has a charge of 0, right? So it has a charge of 0. Because all atoms on the periodic table are going to be neutral unless they form an ion, which we're going to talk about in a second. Because I remember him teaching you guys about ions, right?
And ions and ions, yeah.
You know, he did a great job, you know.
You had a pun, but I forgot the pun.
Oh yeah, the cation.
Oh,
Okay,
it's pause, there you go.
so if we have an ion, it's going to have a charge associated. Metals are typically positively charged. There may be an exception every blue moon, but for the most part, 99.99% of the time, they're going to be positively charged, right? Unless, or neutral, one or the other. Neutral or positively charged. Okay, now if there's a positive charge associated with it, it's based upon how many protons and electrons you have, right? If it's a positive charge, that means you're losing electrons, right? And as the pun was saying, if you're positive, it's called a what? Why is it called a cation? Come on, say it.
Because it's positive.
There we go. I get it, right? There we go. Because it's positive, right? So we know that this is a cation. Cation is a positive charged ion. Okay, so how many protons do I have here? 74. How many electrons?
72.
Oh,
I have 72, right? Because it's positive. It loses how many electrons? It loses 2 electrons. Okay, so if it has a charge on it, a +2, right? That means that we're losing 2 electrons. That means the protons outnumber the electrons. Okay? Make sense?
so if it has a positive charge, it loses, but if it has a negative, it gains.
That is correct. Okay, you guys ready for the next example? Okay, let's say we have this ion. I mean, this isotope. How many protons do we have? How many electrons do we have?
15.
How many neutrons do we have?
16.
Okay, now let's say we make it into an ion. So now we're going to make it into so it's negative now. A negative ion is called an ion. Okay. Okay, how many protons do we have here?
15.
Oh, I was thinking.
It has 15 protons. I'm going to put a P plus for protons. Okay, how many electrons?
18.
Minus, there's 18. And then neutrons, 16. And not. That's going to be my symbol for neutrons. Okay, piece of cake, not too hard. Right. And so here we're talking about isotopes. Now, when we're talking about the periodic table, we're taking into account that whole average. So we don't have to put this. We just do it like this. So you would write the ion just like this. Right? Okay. And then we would just take the number that we have for its mass, its atomic mass. We round it up to the nearest whole number. Right? So what will be the nearest whole number for the atomic mass for phosphorus?
31.
31. So it just happens to be the exact same isotope, right? Does that make sense? Questions? Leslie? No. No questions? You guys got it? All under control? No problem? Leslie?
Thank you.
Okay, so let's go back to the lecture notes. What other mess we did? Okay, so you guys already know that neutrons are uncharged. They're also a subatomic particle. They also make up the mass, right? And so their discovery is accredited to James Chadwick. Okay, we also know that neutrons are found in neutrons. Okay, so let's talk about the nucleus. So the nucleus is going to be the center of the atom, right? It's going to be composed of what again? Protons and neutrons. Now, they're going to be the weight of the atom, right? So the weight is going to be located where? In the nucleus, which is the center of the atom, right? So it's going to be located in the center. Okay, so if we talk about the electrons are going to be in a cloud on the outside. Okay, so they're going to form like a little cloud structure circling the nucleus. Okay, now the diameter of the atom. Now this is the average diameter of like all atoms. Each atom is going to have a different diameter because depending on the number of what again? Well, protons, neutrons, and electrons in this case, because it's the size, and not the weight, the size, right? Okay, so then the diameter of the atom again, this is the average diameter of all the atoms together, is going to be 10 to the minus 10 meters, right? The diameter of the nucleus is going to be 100,000 times smaller, okay? And that's 10 to the minus 15 meters. Okay, so let me give you guys an idea. So if we put a blueberry in the middle of a football field, and you were at the top stands, would you be able to see that blueberry? No, you wouldn't, right? So that gives you an idea. That blueberry represents the size of the nucleus. The football stadium or the football field represents the size of the whole atom. Okay? So in other words, that electron cloud is pretty dense, right? It's pretty wide, I should say, compared to what we see. Okay, so when we talk about the units, right, for an atom, the weight of an atom is determined, called AMU, atomic mass units. Okay, now 1 AMU is what a proton is. 1 AMU is what a neutron weighs. An electron, its weight is going to be 5,000 times less than an AMU, right? So it's really not going to make a difference. Okay, and so if we look at an AMU is going to be 1.66 times 10, 1.6605 times 10 to the minus 24. And the mass of carbon is kind of like the molecule that we kind of base our entire weight system on. Carbon weighs 12, right? 12 AMU, because it has 6 protons and it has 6 neutrons. Right? So the exact mass, if we're being very, very, very exact, is 1.0073 AMU for the proton. For a neutron, is 1.0087 for the neutron. Right? We know the charge of a proton is +1, charge of a neutron is 0, and then the mass for an electron is 0.00055 AMU. Right? So significantly smaller. So that is not going to make a difference, and it's has a negative charge. Okay, so a neutron is a little bit higher than a proton. So we roughly just estimate it, rounded out to 1. But if we wanted to be more exact, we just have to do the calculations. Okay, so the atomic number is going to be defined by the Z letter. So often you'll see in questions, they'll use Z. You notice on the periodic table, you don't have an element for Z, right, by itself. And that's because we always use it to define the atomic number. Okay, what does the atomic number represent again? What was that? You said number of protons. Number of protons. So you said Z. You said Z. Yes, we use Z to sit there, and that's our symbol for it. Okay, with the number of neutrons, you already know how to calculate the number of neutrons, right? Okay, this is just basically showing you A represents the atomic mass, or the mass number, minus Z, and that's going to give us a number of neutrons. Just fine. We've already talked about ions. So the charge on an atom is just going to be the number of protons minus the number of electrons. So if it's a negative number, we know that we have more what? My question was, if the charge on an atom is going to be number of protons minus the number of electrons. So if I have more electrons, then my charge is going to be
Negative.
It's going to be negative.
Yeah.
Right. Because my number of electrons outnumber my protons. Okay. So you notice that we never talk about protons being deficient. Right? You notice that? You never say, oh, we're going to change the number of protons.
I was wondering about that.
You were wondering about that, right?
Yeah,
Why don't we do that? Since you're wondering, why do you think we don't do that?
because it will become different.
Say it again.
It will become a different number.
It will become a different element. So if we had 5 for protons, then that would no longer be permanent. What would that be? If it has 5, it would be boron, right? That is a total different element. It's going to be totally different, right? So that will never happen. Right? The only time it will happen is if we change that element, which we're not going to do it, right? Okay, good. Okay, so we talked about cations and anions. Cations are what again?
Awesome.
Positive, okay, and anions are, okay. So you guys already know about chemical symbols. We talked about that last week, right? So we know what they mean. We know how to write them. We know how not to write them, right? We talked about the little O and the big P and all of that, right? Just making sure I haven't gone crazy. So this here is mercury. Mercury at room temperature is a liquid. Okay. One way that we know that it's a liquid is how. At room temperature. How would we know that it's a liquid? Is there anything that we know looking at our periodic table? Does it look any different than anything else? The color of the letters, right? And then I believe it says somewhere that the colors of those letters. Oh, it's a liquid. There we go. It says it's a liquid, and it gives us an example of mercury, right? So that means at normal temperature, room temperature, it's going to be a liquid. So mercury is unique because it is the only metal that at room temperature that is a liquid. Is there any other metal in this liquid?
Bromine?
Bromine is not a metal.
Oh,
Is it?
no.
Look where it's at.
It's a no.
Okay, it is a halogen. What other family does it belong to? Is it a metal or is it a non-metal? It is a non-metal. How do we know that it's a non-metal? It's in the green. There we go. So you're able to sit there and distinguish based upon your periodic table. You guys have a kick-ass periodic table. I was looking at the one that they used to have about 40 years ago that we have in Fireball, right? The one that they want to put on the wall. And I keep telling them, no, you cannot put that on my wall. And they're like, why can't I put that on the wall? I said, because that periodic table is too old. It doesn't have all the elements, right? Because science has changed over time. Okay. The other reason is because they don't have cool features like that on their periodic table. So I'm not going to put any crap like that on my wall. Okay. So these are some of the common elements. By the end of the semester, you should know all of these elements by their symbol, right? I'm not saying that you should memorize them. You should be using them so frequently that it just sticks up here, right? Because I find that you remember things. And not only that, once you kind of get it, right? Once you start doing it and you use it so frequently, you will sit there and you're like, yeah, I remember it. And then you'll notice that 5 years down the line, 10 years down the line, you'll still remember that because you've used it so frequently that you're like, oh yeah, you know, I know magnesium is Mg, right? I know manganese is Mn, right? It's the ones that are commonly mistaken, right? I know that mercury is H2. Right? I know that gold, hey, you stole my gold, right? So I know those things, right? So the more you expose yourself to it, the more you do the homework, not Google the homework, do the homework, the better off you're going to be. Right? Okay, we talked about isotopes. What is the definition of an isotope again? Okay, there we go. And so this is just showing you one way that they like to write it. So here's an example. We have, what is Mg? Magnesium, that's right. Magnesium. So we have magnesium 24, we have magnesium 25, we have magnesium 26. And that's what their names would be. Magnesium 24, magnesium 25, magnesium 26. We know the difference between magnesium 24, magnesium 25, and magnesium 26 is what again? They're isotopes, but what is the difference between them? It's not charge. The number of neutrons, which boils down to the weight. You're correct. It is the weight. It's also the number of neutrons, right? Okay, you guys are good? You got it? Piece of cake? Good. So you guys already know about this. Man, you guys are on top of things. El fuego. right? Because we just talked about it. We know what the mass number is. We know what the atomic number is. We know how to write the charge. So here's an example of hydrogen. Hydrogen exists of three major isotopes, right? We have protium, we have deuterium, and we have tritium, right? Tritium is in a trace amount. That basically means it's so low that we don't know the exact number, but we know that it does exist because occasionally somebody after every blue moon will run across it, right? So that would be tritium. So it's not taken into account in terms of the periodic table. Man, you got sneezes. You guys cover your faces, but you want to share that stuff. Okay, so we're hoping it's just allergies. Okay, so here's the example. This is probably where I got that 99 from earlier, right? So it is, I'm looking over here, it's not over there. Okay, it is 99.989% abundance of hydrogen or the protein, right? So that one weighs 1. So do me a favor, multiply that by that percentage. And then multiply 2 by 0.0115. Well, you can actually use those mass numbers that they actually have there. That would be the easiest way.
You see, add or multiply?
You multiply it.
Okay.
So you want to multiply it by this one, multiply these by each other, multiply these by each other. And remember, you have to divide by 100 so that you end up with decimal part of it.
I see.
Since that's percentage, right? Okay, so same thing. And then add them together. What do you guys get?
Really long numbers.
Shouldn't be too long.
One point zero three zero five.
1.03.
Oh,
Double check, please. I've already made one mistake, all right?
What is this trace? I mean,
Trace, you don't take into account because it's so little that you're getting it. Really, really. What did you forget? What did you? Yes.
I got boys. Yeah.
1.0. Yes. You're working on it. So you want to multiply on this one first? That one? Yes, sir. Take into but that is the that's 2 minutes. So that should be 1, 2. So that should be 1. And you just have 0, 0, 7. Looking in those calculators again, how you're like forgotten those lessons that first week, second week. You multiply the mass by the percent abundance, but you want to change that to a decimal form instead of percentage, right? So you should be 0.999. Yep. That's calculator. Jealous. Girls dressed up today. Girls dressed up today. Got a haircut and everything.
That's right.
You got a hot date after this?
They give me like 2 rounds. It was like some 83,
Okay. Yeah. Is everybody good? Everybody got it? Yeah. And so it rounds up to what you see on the periodic table. What, 008? Okay. So I knew it wasn't crazy. I just used the wrong numbers for the wrong one. Wrong isotopes. Too many isotopes in my head. Okay. Preguntas. No questions? Cool. I like no questions. We can move on to the next 50 subjects. Ready? No, but yes. Yeah. Okay, so we already talked about the atomic mass, right? So you guys already know what it is. I'm going to tell you about it. Okay. I already told you how it's calculated. So that average mass is what we see on the periodic table. I've already shown you how to calculate it. So here's another example. So if we have 19.9% B10, right? Boron 10, which has a mass of 10.019129 AMU. And then we have boron 11, which is about 80.1% with a mass of 11.0093. Right? So if we multiply this by that percentage, and then we multiply this guy, this mass by this percentage, and we add them together, we get the average mass of our atom, which is 10.81. Is that what you guys see on the periodic table? Yes. Yeah. So you essentially get what you get on the periodic table, right? So that's how you'd calculate this, right? That's how we calculate it. So we initially got the mass, again, from mass spec. I'll show you that in a second. Oh, mass spec, yeah. Ahead of the game. Okay, so in the case of the mass spec, what happens is we take our sample, we vaporize it. We put up so much energy in it, right? And then we also give it a little bit of charge. And then we shoot it through this ion accelerator, right? So we get these ions, we get it all charged up, goes to the ion accelerator, put it in a magnetic field. Now, a magnetic field is going to cause us to do what again? Positive, negative, what is that?
Either repel or attract.
It's going to either repel or attract, right? So in this case, it's going to be that positive side, it's going to go towards that. So it's going to move down here. Then we have our detector. So then we're actually separating it based upon its size and charge, okay? So here we have zirconium. So there's zirconium. Zirconium has a lot of ions. There's zirconium 90, there's 91, there's 92, there's 94, and there's 96. Right? And it's able to sit there and figure out how much abundance each one of those ions, each one of those isotopes we have, right? So roughly, we have a little more than 50% of zirconium 90. Here, let's see, that's 30, so these are multiples of 10. So then that's a little more than 10% of 91. That's almost 20%. We'll say about 18 probably of 92. We have about the same amount of 93. And then we have like maybe 1 or 2% of 96. Right? And so we can actually sit there and calculate exactly what it is, because they would give us the exact values. And then we would have the weight, the exact weight that's going to be associated. Okay. And so then we could use that to sit there and calculate how much it actually weighs in the gravity. Now, they didn't have a mass spec back in the day, right? So like, a long time ago. So then they have to use other means of doing the calculations. So we were also very limited about the number of elements that they were available. Okay. So molecular formula, right? So molecular formula is that formula Sam? Okay, so the molecular formula so this here represents our molecular formula. This is the molecular formula for glucose. It can also be the molecular formula for fructose. How many of you guys have phones? Your phones, your cell phones. Do me a favor, look at the structure. So type in structure of fructose. And then I want you to type in the structure of glucose. You can Google it now. I'm allowing you to do Google. Okay. Did it crash on you? Crash on you? Oh, yeah, no. Okay. Are they? You want to put money on that? Look at it. Look at the structure. Find the structure.
Starts a little bit.
Oh, but that's not the correct structure. Keep looking. Oh, wait, look down here. There, that one right there. Right there. This one right here. I love touching it. No, not that one.
Oh,
That one right there. That's right. There. Yep, that one. Perfect. Okay. Not that one. There should be one that has both of them. Yeah. So you can put glucose except fructose. So I have one that has both of them. So type of fructose. Yeah, that's the one. Yep, that's the one. You guys make it hard sometimes having things that I can't see. What are those screens?
oh, the screen's.
Oh, yeah. Perfect. Now I can see it. That one right there. Your phone don't like me. Okay, maybe it likes you better. It likes the nails. It's like the nails. Oh, you don't even know. It's like I already know. Good job. It's beautiful. Good job. Get this one right here. So you're looking for the structure of glucose and fructose. No, that's the molecular formula. Look for type in structure. Right there. So right there. That might work. Okay, so you guys take a look at it. You see glucose, you see fructose. What are the differences that you see between them? Tell me, describe them to me.
Fructose starts as carbon to zero oxygen.
Okay, now we want to talk about the structure.
Oh, okay.
We don't want to get into the nitty-gritty. We'll talk about the structure. Is there anything that you notice between the two structures? Yes.
Fructose is pentagonal while glucose is hexagonal.
So one looks like this. And one looks like this. So one has 6 sides and one has 5 sides, right? Now, chemically, right, if we look at just the molecular formulas, they both have exactly the same formula, right? So if you look at it, each one of those corners, right, each one of those corners represents a carbon, unless it has an O in it, right? So do me a favor and count those corners. So this one has how many corners? That's 1, 2, 3, 4, 5. Oops. 5 plus 6. That's 6 carbons. That's 2. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygen. 12 hydrogens. And then that's 1, 2, 3, 4, 5, 6 oxygens. And do the same thing over here. Okay, it's going to be exactly the same number for both of these. Now they're different. These are called isomers. Iso. So iso meaning same, mer meaning unit. Same unit, right? So in other words, it has the same chemical formula or the same molecular formula, but different structure. Different formula. Different structural formula. Okay, so the structure is going to be different. So that's an isomer. Okay, so these are examples of isomers, right? We know that fructose, we get a lot of fructose in what? In glucose. So glucose and fructose are 2 different sugars. We got a lot of
corn syrup.
high fructose corn syrup, right? So we get some in corn syrup, right? And then we also get a lot of it in fruit, right? So we get a lot of fructose in fruit. Fructose and fructose. Because it was first isolated from fruit, right? It typically has more fructose than glucose. Okay. When he doesn't respond. You know what it is? I need your nails. That's what it is. That's why I'm not responding. There we go. Okay. So here's an example. This is methanol, right? This here represents the structure of methanol. This here represents the ball stick model of methanol. And then that is the space filling model of methanol. Why do you guys think we have to show it all 3 different ways? We need to be able to show it all the same ways. No clue? Anyone? First off, why do we have to do, well, we know why we have to do this. Why do we have to do this? Molecular formula. To label it, right? To tell us what it is, right? So we need to know what it is. So why do you think we do the structural formula? Come on, you guys are there. Come on, come on, come on. I know it. I can see it in your eyes. Think. You're overthinking. Don't overthink. Why?
Represent the bonds.
To represent, okay, that's a good one. I'll accept that one. To represent the bonds. Anything else? Structure. How about its structure, right? Its structure. One was a house and one was a stop sign, right?
Yeah.
Okay. So we need to be able to recognize that there are structural differences between compounds, right? 2 compounds may be exactly the same chemical formula, but structurally they could be different, and they would have different responses. Like for instance, in your body, glucose is processed differently than fructose. Well, fructose is phosphorylated first, actually glucose is phosphorylated, but it's phosphorylated in a different spot. And then it's modified, fructose is changed to glucose so that we can actually utilize it in our system. So then we actually have to make some modifications for that to happen. It has to be cut and reorganized, right, for our body to process it. Okay. If you didn't have that gene to do that processing, you would be able to process fructose, right? And you poop it out. There is a rare disorder that is the case, but most people are okay. Okay, so we know that elements are going to exist in molecules. You already know what a molecule is, right? We already know about the diatomic elements. I don't even talk about it. What are the diatomic?
There's a
There you go.
Have
What is it?
There.
Have no fear of ice cold beer. That is correct, right? And we also know the ones that are polyatomic are, bless you, everybody sees it. At least you covered it. Okay. Polyatomic. Phosphorus and sulfur. It's right up there, yes. Good job. Phosphorus and sulfur. Okay, so here's sulfur, right? This is what sulfur looks like normally. The hot mess, right? So when it's bonded to itself, it's bonded like this. It's a nice little circle, right? A string structure. Okay, this here's the ball stick model of it. This is the space filling model of it. Okay, so you guys also know that sulfur is very aromatic. It smells a lot, right? It does smell a lot. But there's something also nice about sulfur, right? It can also hide smells as well, right? So it's often used for that. So that rotten egg smell, right? Sulfur, right? You guys smelled that before? You guys, Hanford's water used to smell like that all the time. They've been treating it for a while. It's still, when you drive by Costco's, you'll get a whiff of it, right? You'll smell it there. Okay, so this is one atom of hydrogen. This is two atoms of hydrogen. You see that we use that coefficient, right? Coefficient versus subscript. When they're combined together, when they're bonded together, we write it as a subscript, right? And then if we have a coefficient and a subscript, that basically means we have two of those that are bounded together. Does that make sense? So it's important that we understand this, because this is, again, one of the most commonly made mistakes. Misunderstanding what the coefficient means versus the subscript. Okay, so we're on empirical formula. Okay, so let's go back to the board. So this here is called the molecular formula on the board. I know you guys can't see. Let me put it on that thing. We'll come back. We'll come back to this. Then I think we're gonna have to take a potty break. So, yes, it is. Okay, so this here is called our molecular formula. Now, the empirical formula, it tells us bare minimal the ratios of each of the elements to each other. Okay, so for instance, so the empirical formula gives us the lowest common denominator. So if I divide, if I had a number to divide these numbers by, what would I divide them by? 6. I would divide them by 6. So if I divide this by 6, that would give me 1. If I divide 12 by 6, that'll give me 2. And then if I divide 6 by 6, 1, right? So my empirical formula is going to be CH2O. So when we're working like with the mass spec and other types of instruments, a lot of times what it'll give us the relationship between that compound. So like for instance, the mass spec will actually vaporize it so much that we break every bond. And it'll let me know that I have that ratio of 1 carbon to 2 hydrogens to 1 oxygen, right? It won't let me know that I have 6 carbons, 12 hydrogens, and 6 oxygens. I'm gonna have to figure that out. So I'll have to run an algorithm to determine what compounds are gonna have a 1 C, 2 H's, and 1 O, right? And so an algorithm will give me all of these different compounds, and then based upon some other characteristics, I can tell you what it is, right? And sometimes if you have a good mass spec, right, we hook it up with something else like a liquid chromatograph, then we'll actually have, it's called LC mass spec, or a gas chromatograph, a GC mass spec. We're able to sit there and distinguish between what that compound is, what's in it, and then also how's it bonded together, how it's behaving. So we can get some other characteristic out of it. Maybe it's boiling point. Maybe it breaks down to a couple of peaks when it breaks down. And so from that, I can sit there and distinguish between glucose from fructose, okay, with a little more information, okay? So, but we know empirically, right, the empirical formula for glucose and fructose are exactly the same, right? So this is going to give us a minimal amount of information, the empirical formula. L. Okay, the empirical formula is going to give us a minimal amount of information, but it does give us the relationship between each of those atoms to each other, right? And that's what we want to get out of it, pheromones. Okay, does that make sense? You guys have that look again. Make you worry when you have that look. You guys are doing this and get a little bit of a knot, not a real knot, and be like with the bobblehead knot, you know?
Like sugar.
Like sugar, yeah.
Not like sugar, like sugar. You understand?
You understand? Okay, so let me see if I can explain it a little bit better, right? So here is the molecular formula for benzene. Benzene forms this nice little ring structure. I'll show you what it looks like here in a minute. Now, I just want to figure out the relationship of carbon to hydrogen for benzene, right? So then what I'll do, I'll divide it by a common denominator, right? So the common denominator would be here, what? 6. So if I divide both of these by 6, I'm left with just C and H. So that would be my empirical formula. Okay, do you guys get that? Okay, so acetic acid, C2H4O2, right? So in this case, I divide it by 2. So then I get CH2. Oh my God, that's the same thing that we got over here, right? So then if I'm just given the empirical formula, could I tell you if it was glucose, fructose, or if it was acetic acid? No, I couldn't, right? I need to find out more information. I would need more information to sit there and make that distinction. So what I'm saying is that some instruments, some of those dated, obsolete machinery that they want us to use in this class, right? They're dated, right? And they only give us the empirical formula. We need more. We'll need more to sit there and figure out what it is. And that's why I tell them they need to buy me another machine, right? I'm like, yeah, you need to buy me this. And I have to make this argument on Wednesday, right? This will be my example that I'm giving in class, right? I'm giving them a lecture. Well, they're going to love it. So this is the reason why we need newer machinery, because back in the day, this would have been fine. This would have been acceptable, right? Because then you would have done, you had months and months and months to do the experiment to figure out that it was acetic acid instead of sugar. Well, we don't have that time anymore. Time is money, right?
Yeah.
Time is money. We need to make money, right? You guys don't want to be here and take 5 classes of just learning how to manipulate certain chemicals where you can sit there and do it in 15 minutes, right? You want that new piece of equipment so you can sit there, okay, we got this data, we just need to analyze here. Okay, this is what it is. Bam, that's it. Okay, damn nails. I need them. I'm gonna get some. I'm telling you. Where do you get your nails done?
Over there by Subway.
By Subways? Okay, so I'm gonna be going to get my nails done. Okay, so this is an example of a benzene ring, right? So I told you, I showed you what benzene looks like. So this is the what again? What structure? It's structural. Okay, so it's called the structural formula, right? Then this is ball and stick, and this is, and this is what it actually looked like in real life if we have enough of it, right? So this allows us to sit there and look at a single molecule. Where if we were looking at it in real life, we'd have a little bottle of benzene, right? And you'd be like, I can't tell the difference. Can you tell the difference how it looks in that bottle compared to over here? So why do you think we use that?
Clarify which.
So why do we?
Clarify which element it may be.
Okay, to clarify which element it will be, right? So by looking at the structure, we'll know what benzene looks like. If somebody gave us a clear liquid, you'd be like, what the fuck is that, right? It's not labeled. Is that labeled?
No.
Right? You would know, because you know why I say, look at it. Okay, that's benzene, right?
No, it looks like water.
It looks like water, right? The way that you could tell it's benzene, right? You wouldn't know, right? So we need to sit there and put either the symbol on it, the structural formula, or the molecular formula, or the name, right? So we would need to label it, right? So for us, the reason that we use models and we use those structural formulas, it allows us to sit there and recognize what that compound looks like. And from that look, we can kind of guess on how it's going to behave, right? So this is vinegar, right? Acetic acid is vinegar. Now, we talked about vinegar and glucose having the same empirical formula. Now, let me ask you this. How many of you guys put vinegar in your coffee? Anybody? Anybody put vinegar in your coffee? Why don't you put vinegar in your coffee?
Because it's nasty.
Because it's nasty. Vinegar is great on pickles, right? But to make pickles, I should say. But it's not so good in coffee, right? Because we want something a little sweet, you know? Is that true?
No.
Yeah.
I like bitter coffee.
Yeah.
You like bitter coffee? Well,
Yeah.
maybe add some vinegar to your coffee. It'll be bitter for you, right? So the thing is that if the empirical formula says that they're exactly the same thing, but we know that they're not. They have different properties associated. Sugar is nice and sweet, delicious. Vinegar is not nice and sweet. It's a little sour, right? A little bitter, like you like your coffee, right? Maybe you should add some vinegar. Okay. Now structurally, they're different as well too. You guys already saw the structure of glucose and fructose, right? This is the structure of acetic acid. They look nothing alike, right? So isomers, what are isomers again?
Same.
There we go. Same chemical formula, but different molecular structures, right? You guys got it. Is it engraved? You remember it? You guys look so poor things today. You poor little things. So tired. It was a rough weekend. I turned it up last weekend. That's what it was.
Yeah, our energy guy is in here.
Your energy? I know, he gets us all pumped, doesn't he? Come in with this big old jug of water, where's he? Anybody text him, hey, where you at, right? Here's another example, right? So these guys, they have the exact molecular formula, same chemical formula, right?
Yeah.
But they're different. Can you see the difference between those two? What is the difference? Everybody said, yeah, I see everybody saying nothing. And then when I ask what's the difference, nobody says anything. Look at this. Yes, sir.
So right after, I don't know how to explain, but after see the middle.
Right here.
Yeah,
in this area.
it goes, yeah, it changes right there.
Okay, so we have some change here, right? Because we have a carbon bonded to another carbon here,
Yeah.
right? Where we have a carbon bonded to an oxygen here,
Yeah.
right? Okay, so that would be a difference, right? Any other differences you guys see?
The oxygen and carbon switch places.
The oxygen and carbon switch places. So we have it flopped over here, right?
Yeah.
Okay, so these are examples. They're two different chemicals. They do not smell anything alike. They do not taste anything alike. As a matter of fact, methyl formate is actually a little bit of a poison. It's horrible on you. But you guys, we have acetate, right? We drink acetate, right? We have vinegar every once in a while.
Oh, yeah.
Pickles, or sometimes we cook with it, right? You don't cook with vinegar? Yes, you do. I'm sure you do. You just don't realize it. I know I cook with vinegar, you know? And then when you want to get rid of that fishy smell, what do you use? You use lemon or you use vinegar, right?
Yeah.
Yeah, you pour vinegar down the sink, you get rid of that fishy smell, right? Or you put a little bit of vinegar on your fish. Fish and chips, you know? The vinegar,
yeah.
bomb, you know, yeah. Put it in your fries, you know, because then it's like, what is that? The salted vinegar flavored potato chips,
Yeah.
right? That's
yeah.
the fries. Where do you think they get that from, right? Fish and chips. Okay, so here's another example. Then I think we're gonna stop right after this example. Okay, so this guy, this is mint. I grow a lot of this. I used to grow a lot of it. This summer, nothing grew. Everything burned up. But so mint, you know, everybody knows what mint smells like, what it tastes like, right?
Yeah.
Okay, minty fresh. So this here is it's basically a poison that they use for insects, right? And so two different ones, but chemically, if you look at these structures, right? They're both called Kavon, right? One is a plus and one is a minus. Now the difference between these are called spatial isomers. So do me a favor, you have your hands, put your hands up. Wake up, don't fall asleep on me, right? Okay, you have your hands up, put your hands up, everybody hands up, right, hands up. Okay, everybody has hands up. Okay, now do me a favor, do like this, pray that you pass this class. Jesus, please, let me pass this class. This is a rough class, I need a pass, right? Okay, now if you look at it, look at your hand, right? Perfect fit, right? Your hand ain't perfect?
Bigger than one.
One's better than the other? Okay, I will have to figure that one out here in a minute. That's a whole nother topic. Okay, now you look at it, they are a perfect fit. They are mirror images of each other, right? Now do me a favor, do this. Put them palm up. Okay, are they mirror images of each other now?
No.
No, right? They don't fit perfectly, right? You got your thumbs on each side, right? So that's what a spatial isomer is. This is an example of a spatial isomer, right? We put them like this, they're perfect. But we actually put them right on top of each other, they're not, right? They're different. So take a look at that. Can you guys see the spatial isomer, the difference between the two?
They're
Weird.
They're mirrored, right? Okay, just like our hands. Okay, so this is another example of an isomer, right? If you look at it chemically, they're exactly the fucking same, right? But they're just mirrors of each other. They're going to behave differently. One again is a poison. One is smells, it tastes delicious, right? Mojitos would not exist without the mint. You need the mint for the mojito, right? It is bomb, yes, right? Okay, so this is another example of the isomer. Okay. You guys, you have got a minute in you. We can get through this in a minute because we've already gone over most of it. So the periodic table has changed quite a bit. One of the things that we've noticed about the periodic table is it used to have different names. So we've kind of incorporated some of those different names into our symbols. So like for instance, sodium. Sodium is Na. It doesn't start with an S, right? So its old name was like, was like natrium, okay, and then potassium was like, I can't remember what the K stands for, but old age, this is the old periodic table, right? And I used to do it by weight. So the first periodic table was all done by weight. But if you guys look at your periodic table, if you look at chromium, look at cobalt and nickel, right? So it used to be by weight, so it was organized initially by weight. But you look at cobalt and nickel, right? Now, cobalt has a smaller atomic number, right? Is that true? Am I lying? Cobalt has a smaller atomic number than nickel, right? Now, but look at the mass. Which one is more? Cobalt. Cobalt weighs more, right? So the old periodic table would have it organized by mass in terms of increasing mass. So they have to switch that. They went back to the atomic number. They went to the atomic number because it makes more sense, right? It's going up. It's constantly going up in terms of the atomic number. Right? So modern periodic table, we already talked about it. At the very top, we have our groups. On the side, we have our periods. Okay, so if you look at this periodic table compared to your periodic table, you'll notice there's some changes that have occurred, particularly in this area, right? So there's 3-letter words because we didn't know what they were. So we just use this U at the beginning, and it'd be UN, UNP, whatever. And so those guys were unfounded or unstable initially. And so they weren't declared to be stable until they got to a certain point where they were stable for so much time. Now, all of these guys here, these ones that are in parentheses, all of those are basically man-made, right? The other thing about them being man-made, that is the guesstimated weight, because they're only stable for a certain amount of time at that particular weight. They're not maintained stable throughout the entire day. Okay, and so that's why you'll notice that. You'll notice that here with a lot of the lantanoids and the actinoids happening as well too. You'll see a few of those that are in parentheses as well too. But your periodic table has developed quite a bit, right? Notice some of those changes.
Yeah.
So, like for instance, you guys have NH. There's no NH up there, right? You guys can find NH. Where's NH located? Give me the period and the group. 13 and 7, right? Now we go 13 and 7 here. 13, 7, right? So it's developed. Science is changing, right? Science is not a static field. So we're learning new stuff. So every time I put this old one up, it's already dated. So we have to get a new one, right? Okay. So that's why I keep telling them, get your old stanky, periodic table off my wall. Okay. So let's go. So you're able to distinguish between your metals and your non-metals. So the characteristics of metals, they're going to be shiny, they're going to be malleable, they're going to be good at conducting heat and electricity. What is malleable?
Bendable, you can reform it, reshape it.
Okay, that's good. I like that. If you have somebody who's worked with metals, obviously. Okay, so non-metals, they're going to be dull. They're going to be poor conductors of electricity. Okay, and metalloids can have characteristics of both the metal and the non-metal. Okay, they're going to be able to conduct heat and electricity, right? And they're going to have properties of both that metal and the non-metal. Some of them are going to be a little bit shiny every once in a while, and some of them are going to be, it's like that. Okay, so there's the main group. Now the main group, or they call it the representative group. The main group is groups 1, 2, 13 through 8. Now this was called the main group because before there wasn't a lot known about transitional metals and post-transitional metals and all those things. So as time went on, we know a lot more about it. So they don't distinguish between the main group and our other groups anymore. We just have that whole group structure. So in the old days, the main group would be labeled 1A, right? And 1B, and then 1C, and all of that stuff. And so all of those represent the main group. 1A, 2A. But we no longer do that now. You notice we just have that number, the groups up top, we don't see it anymore. The old periodic table used to sit there and distinguish between the main group and that of the transitional metals, that group E. That's what I'm group E. That part in red, the transition. Okay. So we know characteristics. We know that alkali metals, alkali and alkaline. Alkali are going to be very reactive. Alkaline is going to be less reactive, right? Their names kind of tell us that. Alkali. Doesn't that sound like you're going to kick somebody's ass?
Yeah.
Alkaline, right? Where alkaline is kind of nice and, so we have the picogens, we have the halogens, we have the halogens, and we have the noble gases. I did show you guys the movie with the noble gases children.
Yeah.
Yeah.
No, you didn't.
Yes, I did.
No, you didn't.
Yes, I did. Want to argue about it? We can argue all day.
I just wanted to see it again.
I know. Okay, so this is just showing you that. You guys have a nice periodic table that makes it clear. Okay, so I think this is a good part, and then we'll come back to ionic compounds. That's what he was going to do. He was ahead of the game. Okay, so we'll pick up on our ionic compounds. So let's take a, we'll say a 15-minute break, and I'll see you guys back here in 15 minutes. That gives me enough time to hopefully remember what I'm doing for your lab, but I think you have to print it out. Okay. Everybody got the handout? Yes, sir. Good, good. Okay, so we're gonna be talking about the mole. Okay, so recording. Okay, so what do you guys know about it?
1 mole equals to 22.4 liters gas of.
Okay, so we've got to work on that a little bit. So let me tell you about the mole. Okay. Okay, so before we tell you about the mole, let me talk to you guys about ounces. Not ounces, sorry, wrong thing. Dozens. So, what do you guys know about the dozen?
It's fall. It's 12 dozens.
It's 12 dozens. So you're saying 12 is a dozen. That's what you're saying. That's what you're trying to say, right? Are you sure about that?
I hope so.
Okay. Did anybody agree with it? This for me. You guys agree with him? You want to argue with him about it? Don't give him a hard time. So everybody knows what a dozen is, right?
Yeah.
Are you sure?
Yeah.
Okay. So you're saying a dozen equals 12. That true? Okay, good. So if I tell you I have a dozen shoes, how many pairs of shoes do I have? So if I have a dozen wives, how many wives do I have? 1. I just said I had a dozen. Okay. So I have 12. I have 12 wives. Gotta work on that. Okay? So if I tell you I have a dozen of kids, how many kids do I have? 12. So I know that 12 means a dozen. Right? Okay, for the mole is very similar to the dozen. Only thing, a mole, 1 mole is going to equal 6.022 times 10 to the 23rd. Okay, so 1 mole is 6.022 times 10 to the 23rd. So if I tell you I have 1 mole of girlfriends, how many girlfriends do I have?
6.022 times 10 to the 23rd.
So if I tell you I have a dozen boyfriends, how many boyfriends do I have?
Oh, wait, wait.
If I have 1 mole of now we got a mole of boyfriends, how many boyfriends do I have?
6.0.
That's right. So if I told you I have a mole of troubles because I have boyfriends and girlfriends, how many troubles do I have? 6. Okay. Now if I told you I had a mole of kids, how many kids do I have?
6.022 times 10 to the 23rd.
Okay, so you guys understand 1 mole equals 6.022 times 10 to the 23rd. That's it, right? Okay, now that is quantity, right? Because we could simply say it's quantity, just like the dozen was. Dozen means 12. That means I have 12 figures. So in science, if you think about what we're doing, we're working with quantity, right? And since if we say we have 1 of those, right, we can't see what 1 looks like. We often will have to work with a lot, right? So a mole is a lot, right? So let me give you an example. If we have 12 grams of carbon, right? Let's say carbon is just coal, right? You guys are familiar with that. If I give you a lump of coal that weighs 12 grams, right? That would just be coal. That's 12 grams. Okay, that would equal a mole. Okay, so if you look at your periodic table, the mass that we have, right? Carbon weighs. How much does carbon weigh? It's grams per mole. So 1 mole weighs 12.011 grams per carbon. Okay. Now that would be how many molecules or how many atoms? Atoms. If I have 1 mole, how many atoms would that be? carbon.
6.22 times the 10 to the power 23.
6.022 times 10 to the power of 23. I just told you that, right? We're overthinking it, right? You're overthinking it. Because I threw in that mole, gram and mole, right? So we can convert mass into quantity, right? Using the molar mass. What you guys see, that 12.011 grams per mole, that is called the molar mass of carbon. Molar mass. Okay. Why do you think it's called the molar mass? Molar mass.
You get that by dividing by 1 mole?
That's right, because we get it by dividing by 1 mole, right? So hence molar mass, right? So it's that mass per mole. You guys see that? Okay. Okay, so this is a conversion factor. It allows us to change mass into quantity, or in this case, specifically moles. Okay. You guys with me? Bobblehead, right? Bobblehead. Okay, don't worry about it. You'll get there. So I know that if I have 12.011 grams, I have 6.022 times 10 to the 23rd atoms of carbon. Because I know that that's 1 mole. Okay. So if I have 9.0122 grams of beryllium. Beryllium. How many atoms would that be? Because again, it's its molar mass. So in the periodic table, it gives us its molar mass, right? So what is the molar mass of beryllium?
9.0122.
9.0122. So if I have 9.0122 grams of beryllium, that's going to be 1 mole.
Yeah.
So then how many atoms would that be?
You just divide the by 1.
Yeah. Because isn't it per mole? So I have 1 mole. If I have 1 mole of it, right? So how many atoms would that be? Gotta say it loud because I can't hear you. Can't hear you from right there. Say it louder.
6.022 times 10.
That's right. It'll be 6.022 times to the power of 23 because we know it's grams per mole, right? What is the weight of beryllium? Okay, so that's how much we have, right? And that's per 1 mole. So that means how many atoms of beryllium do I have in those 9 grams? At 9.0122, right? 6.0, yeah. Okay, so I have what 1 mole would be, right? Do you understand? You're not getting it? Okay, let me see if I can explain it to you a little bit different. Let's take a step back, right? So 1 mole equals 6.022, right? Now, our periodic table is every atom has its own mass, right? So let me put it like this. Okay. I make a bomb mass sangria. You guys had sangria before?
No.
You ever had sangria before? Like sangria? If you like red or you like white? So,
Red.
you like red sangria? Okay, so let me tell you about my bomb mass sangria. Right? So I have apples. Apples are about this big, right? Give or take. My apples are big. So I like the Honey Crisp, they're sweetness in them. So I take two, write it down. You're gonna write this down. I take 2 Honey Crisp apples, and I cut them all up. Like, you see them and everything like that. But I take 2 of them, right? You got that? Okay, now I take strawberries. Now strawberries are about that big, Now, do apples and strawberry weigh the same?
No,
No, they don't. Why don't they weigh the same?
one has more mass, one's bigger.
Okay, one is bigger than the other, and it's an apple and a strawberry. They're two different fruit, right? So when we're talking about these elements, these atoms, are they not different?
Good.
Do they weigh differently?
Good.
Yes, right? And so what we're saying is that even though we have a mole of them, right? A mole of apples and a mole of strawberries aren't going to weigh the same. They're going to have two different weights associated with it. Okay, so beryllium weighs, and that's going to be for 1 mole, right? Okay, now carbon weighs, okay, and that's going to be for 1 mole of carbon. There are two different weights for 1 mole. Quantity wise, they're exactly the same, but they're two different weights. So if I told you I wanted to put in 2 strawberries, you look at me like I'm crazy. Why would you put 2 strawberries in the same grid, right? It doesn't make sense, right? Okay, quantity wise, 2 strawberries and 2 apples, quantity are the same, right? But mass, they're quite different. Okay, does that make sense? Okay, so back to my sangria. You guys want to know about my sangria recipe, didn't you, right?
Yes.
So I forgot to tell you the part, right? So I get a bag of frozen strawberries, right? Don't get the fresh kind, get the frozen kind because they help cool everything down and they absorb the liquor so much better, right?
All right.
Because this is the secret to a good bomb ass sangria. What you need to do is you're gonna get a quarter of a bottle of vodka. Right? You get the cheap kind, you don't have to be the good kind, just a quarter of a bottle.
Can we
Okay.
like strawberry flavored vodka or just drink
It can be strawberry flavor if you want a strawberry flavor. That's actually a good idea. Try that. So you pour it in there, right? Okay. Now you put your strawberries in there. You cut up your apples, those 2 apples that you're putting in there. You'll put those in there. Now I like plums. I'm big on plums, right? You want to get them a little bit firm, right? Get them firm. Cut them up. You're going to need 3 plums, right? They're going to be juicy plums, but they're going to be firm, juicy plums. Don't get the loose ones, right? Then you're going to get a bag of blueberries, right? You want to get the smaller bag of blueberries, right? Smaller bag of blueberries is going to be roughly anywhere from 30 to 45 blueberries. And you're going to put them in there. Again, you want them to be frozen, right? That's kind of frozen. Everybody's getting this down, right?
Yeah.
Okay. So what did I tell you I'm getting? What did I say I'm getting you so far?
Blood strawberries, apples, yeah, berries.
Okay, you got quantities for it.
Strawberries, a bag.
A bag. So in a bag, there's going to be anywhere from 15 to 20 strawberries, right? They're going to be pretty plump, right? Okay. Okay, you got that number though, right? Okay. So I also throw in a peach, right? And I try to get the reddish peach. Have you guys seen the red skin peach?
Yeah.
Okay, so you want to get that. And then I get a blood orange. I get 3 blood oranges. Got to have some citrus in there. Makes everything taste better. Cut up your blood orange, right? Put it in there. Now at this point, my sangria is going to be like a big old tank. It's pretty neat, right? So if you guys think about how much fruit I'm putting in there, I put in a lot of fruit. Now I have to top it off because sangria is best in the summer. In the winter, it's okay, but in the summer, it's the best, right? The fruit for summer is watermelon. Either watermelon or a nice honeydew melon, right? Honeydew is good for the white, but the watermelon is great for the red. So you can't use the whole watermelon because watermelon's way too big, right? So we're gonna have to cut it up to like a little bit, the fifth of it, chop it all nice up, put it in there, and then you pour in. You can use a fruit wine, or you want to use something like a Merlot, something that doesn't have a lot of spice.
You're right, Marlo's.
Merlots, they're even, right? Or a nice fruit wine. I make my own fruit wine, so that's what I typically use, right? So then I'll pour a bottle of fruit wine in there. And then I'll put it in the refrigerator, let it sit overnight, and then I serve it to my guests, right? Now, when you serve it to your guests, you want to put some ice because you want it to make it last a little bit. You want to throw in some of that fruit. That fruit has absorbed the vodka. That's why you put it in there first before you put it in the wine. You let it absorb. And so most people eat the fruit because the fruit is what the best part of sangria, right? So they start eating the fruit and they start filling it, right? And then they drink a little bit more, and they drink a little bit more, and more. By the end of the night, everybody's loving your sangria. It's the best damn sangria in the world. Listen, that's it. Oh, I forgot one more thing. You know that concentrated juice?
Yeah.
Okay. So what you do, you take a quarter of that. Okay? Now, I want you guys to think about it now. Think about what I just told you. Everybody got that written down, right? Got it written down? But you should, right? Because you want to make this, because I'm telling you, it's the life of every summer party. Let me tell you. And I'm gonna come to your houses to taste your sangria, make sure it's the par. Like I can tell you what's missing from it too. Okay, now, did I ever say I want you to weigh something? Right? Did I say that once? Not once did I say I need you to weigh something, did I?
No.
I told you quantity, right? Or, you know, is it a quarter of this, or, you know, but it's quantity. You know, basically it's quantity, right? If you think about science, we use quantity all the time. It's very rare that we say, you need a pound of this, and you need a pound of that, and you need a pound of this. The only thing I know that they ever say you need a pound of something is when they start talking about, well, meat and a pound of cake, because it's based upon a pound of everything. You're supposed to put a pound of flour, a pound of sugar, a pound of everything. That's the only thing, right? Now, everything else is quantity. You talked about eggs, 3 eggs, right? Yeah. A box cake, 1 box cake,
Yeah.
right? It's quantity. When you're doing a chemical reaction, it's based upon quantity, right? So you need to be able to convert mass into quantity. How do you think you convert mass into quantity?
Moles?
That's right. Or the
Doesn't?
molar mass.
Mass?
Molar mass, right? Because you're changing mass into quantity. So if you have mass, you're able to use that as conversion into quantities. I know it takes you a long way to get to the point, right? But you got a bomb ass sangria out of it. You got to appreciate it, right? And you'll never forget about molar mass if you think about it, right? Think about that bomb ass sangria.
We'll try this on.
Try it and let me know how it goes. You better say this on too. Okay, so let's talk about how can we use moles and molar mass, right? Because we know a mole gives us quantity, right? It tells us how many atoms there are, or how many particles there are, or how many electrons there are, how many girlfriends there are, right? Shitload of girlfriends, right? So I want you guys to think about how many we're talking about, okay? So if somebody is going to give you, not me, because I don't have it, but somebody can give you $3 trillion or 1 mole of pennies. Now I want you to think about it before you answer. Which one would you want? Right? $3 trillion for a mole of pennies. Now, being a true-blooded American person, which one would you want?
$1 trillion because we don't understand what moves.
Okay, wait, not that true much of it. God. Man, you're making this money that I've earned really hard.
Penny's digital at least.
What was that?
The penny's digital.
They can be digital.
Okay,
Okay.
bowl of pennies.
You'll take the pennies, okay? And ask why here in a minute. Anybody else? Well, we know what he's gonna take.
Multiplied 1 cent times 6.002 times or times 10 approximately 3, and we probably figured out that 1 penny is probably worth 1.
Okay? So which would you take?
I don't want to do math, so I'm still thinking.
Oh my gosh.
You asked for the American choice.
Oh, yeah, I did ask for that. I asked for that myself. I set myself up for that. Wow.
It would be kind of hard to pick because like about 100 pennies makes $1.
Okay.
So, like
That's just
I would have to
like
think about
2
it.
decimal points though. Or like, that's just with decimal points over.
Okay. Okay, so we said hard to pick. In other words, you want to be indecisive. You're one of those, okay, that's good to know. Okay. You don't know. Come on, this is your answer. It's what you think, right? It's not what I think. I'm judging you anyway, it don't matter, right? So go ahead, tell me the answer. One or the other. Or you can just take neither. I'll take neither. I'll just be poor the rest of my life. That's fine, right?
Whichever's more, I guess.
Whichever is more.
Uh-huh.
Okay, so which one do you think is more?
I have to do the math, but usually it always comes out to the one that's the pennies.
The pennies.
Yeah.
Okay, the pennies. You think the pennies? Over here? Pennies, pennies, pennies.
I'm doing it with the trillion right there.
You're gonna go with the trillion?
Yeah, I'm just going for the trillion.
Okay. Pennies. 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 Okay, so let's do the math.
I did it. I did the math and I still got 6.2 times 10 to the 20th power.
Okay, wait, hold on, we'll get there. We'll show you how to convert it. Okay, so we have 3 trillion, right? So that's 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 3 times 10 to the 12. Okay, now if we go with 6.02, 2, and 6 pennies, we know 100 pennies is going to equal $1. So we divide this by 100, so that's 6.022 times 10 to the 21st power dollars, right? Which one is more? The pennies. Oh, it cut off. Okay, I think it does that. Let's see if I can move it over. Won't go any further. So I'll stop writing all the way over here. Write it down. See, that would solve all my financial problems. Solve mine, yours, and everybody else's too, right? So you tell them, anybody, I'll take that molar pennies, right? Anytime that you want to give me a molar pennies, I'll take it. Okay, I'll count them myself too. You know, I'm not worried about it. They take me forever, but okay, so you get an idea of how many we're talking about, right? Because literally an atom is so damn tiny, right? So it's going to take a whole bunch of them for us to actually see it. Okay, so that's why we need so many to make it visual, right? You can imagine how many truckloads, I mean, a shitload of trucks to sit there and take all these pennies to the bank, right? So fortunately, I said they were going to be digital, right? But you'd pay them well, right? They wouldn't mind too much. Okay. So when we're talking about that quantity, right? We're talking about a large quantity. That's part of the reason why we use the mole, rather than trying to carry around so many zeros, right? We don't want to carry around that so many zeros. That's also the same reason why we use a dozen, right? A dozen, you know, we have a dozen of donuts, right? You consider, here's 12 donuts, right? Here's 12 donuts, right? It's easier to just say, I have a dozen, right? It's easy. Okay, so the mole is, and it's also called Avogadro's number. That's 6.022 times 10 to the 23rd. Let's name wrong. So it's also called Avogadro's number, right? A lot of people say avocado's number because it looks like it's spelled avocado, but it's Avogadro's. Okay, so 6.022 times 10 to the 23rd. Now that's a mole. Okay, now when we're working with chemical equations, we will talk about the mole. or a mole, or we have 3.2 moles of something, right? Because we're working with the quantity enough that we can actually see and physically work with. Okay, so how you guys doing so far? Pretty good?
Yep.
Okay, so often we so we talk about molar mass. So if we're talking about a compound, let's say sodium chloride, right? So its molar mass, it's a compound. That means we have how many sodiums?
6.0.
Slow down, look on the board. How many sodium atoms do we have there? We have one sodium atom. How many chlorine atoms do we have there? One. Okay, so altogether we have one sodium atom, one chlorine atom. So if we want its molar mass, we just add the weights together. How much is sodium there? I'm hard of hearing. I heard 23 point what? 23, but it's 22.999, something like that, right? So we're gonna round up. 23. Okay, and then chlorine. If I remember correctly, it's like 35.45. So we have these two together. 58.45. That would be grams per mole. So that's how much it weighs. That's the compound. Okay, grams per mole. Okay, so how can I use this? Again, how would I be able to use this? So somebody gave me, and they told me that I have (109 grams of sodium chloride. I weighed out 109 grams of sodium chloride. How many moles would that be? 109 grams of sodium chloride. Yep. Salt. How many moles of salt would I have? 109. I want the number of moles. This is in grams.
Oh,
Divide by the lattice number, but I would divide by the molar mass. Right? So the molar mass will allow me to get the number of grams. If I add the quantity of sodium chloride atoms or sodium chloride compounds, then I would multiply that out somewhere, right? But first, I need to change it to the moles. So if I'm giving grams, I need to change it to moles. I need to change it to a quantity unit, right? 1 mole would be a quantity unit. Okay, so then I want to get rid of grams, so I put 58.45 on the bottom here, grams, and 1 mole on top, because I know that this means 58.45 grams per 1 mole. So per mole means per 1 mole, right? So chloride, sodium is going to cancel out. So somebody do the heavy lifting for me. 1.86. Okay. And then is that the right number of sig figs? Well, it's going to be yes, because you'll never use the molar mass to determine the number of sig figs.
Oh, okay.
So yeah, how many sig figs? 3. So then my answer should have
0.
how many should have? Should have 3. 1, 2, 3, right? And then I know this is moles of sodium chloride. Everybody got that down? Okay, so now we know how to calculate moles if we're starting off with grams. Okay, doing pretty good so far? Okay, so I'm going to introduce you to something else. It's called molarity. Now molarity is going to equal moles of solute over liters of solution. Okay, now what do I mean by that? Okay, so if I have salt and I dissolve it in water, right? Right now, I have 1.86 moles of salt. And I'm going to dissolve that in water. And we're going to bring that water, so solute solution is going to be equal to solute plus solvent. If I'm dissolving salt in water, salt is going to be my solute. It is the one that I have the least amount of, right? And that's being dissolved. Okay, the solvent is going to be water because it's the one that's the most abundant. How many of you guys have made Kool-Aid before? 3 people. You all know what Kool-Aid, 4 people. You all know what Kool-Aid is, right? You know what Kool-Aid is. Yeah? Okay, good. So do you know how to make Kool-Aid?
You get that powder, you have some water, if you're lucky, you have some sugar.
If you're lucky. I hope you have some sugar because otherwise it's not so good, right? Okay. I guess we could add vinegar, right? It tastes the same, right? Oh, okay. I'm just making sure you guys paid attention. Okay, so you have your water, you have sugar, and you have that packet, right? Your solutes are going to be the sugar and the packet. Your water is going to be the solvent because it's what's dissolving everything, right? Okay. Does that make sense? Okay, so usually it's the easiest way of just remembering it. The one that's going to be the most abundant, right? That's going to be your water. That's going to be your solvent. It's usually the liquid in most cases. In most cases, sometimes you have a liquid and a liquid. So, like, how many of you guys have rum and Coke? Right? Rum and Coke. So what is going to be your solvent? And what is going to be your solute?
The Coke is the solvent and the rum is the solute.
That's right. Right, because they give that one little shot of rum and then, you know, and then the rest of it is Coke.
That's like different rolls. That's different.
Whipping rolls, okay. Where you put a little bit of Coke in a lot of, okay, I get it. Okay, so if we're talking about a liter of solution is all of it together, right? So if I say that I'm going to put this into 2 liters, right? I'm going to put a 2-liter solution. So if we wanted to calculate its molarity, that's going to be molarity going to equal at 1.86 moles per 2 liters. Now, here, how many sig figs should I have? 2? 1. I should have 1 sig fig because my 2 liters in this case, right? There's only 1 significant figure. So if you guys do that math for me. Okay, so that's going to be 1. Okay. 1, and it's a capital M, the line under it, or you'll just see in some cases it's just a capital M. So either just a capital M or capital M line. You'll see it both ways. Okay, and that stands for molarity. Okay, so we have a 1 molar solution of salt. Okay. How you guys doing so far? Okay, now molarity is concentration. You got that? Molarity represents concentration. So it tells us how concentrated our solution is. It's only 1 molar. something that's 10 molar is a lot more concentrated, it's 10 times concentrated than that one, right? Okay, so a lot of times we'll be making other solutions and we'll use this one as like a stock solution, right? So we'll use this as our starting point. And so if I wanted to make another solution, let's say I wanted another solution, let's add on to our layers of mess here. Can I erase this down? Everybody got this part? Bring it out. Okay, so let's say I wanted to make a 0.5 molar NaCl solution. Okay, now I know I have a 1 molar NaCl solution. And let's say I wanted to make 50 milliliters. Milliliters of how much 1 molar NaCl solution will I need? And how much water Okay, so let me say that we have this problem. Now, there's an equation. We have C1 equals C2 D2. C1 is the concentration. Initially,
We can't see.
can't see anymore. I need a bigger board. This little, it's not working for me. I have a lot to say. Can you guys see that now?
Yeah.
P1 is the volume. Okay, now C2 is going to be concentration. What? And then B2 volume. Okay, so if we go ahead and plug this in, we have C1, B1. So where is my C1 and B1? Where's that my C2? This is not what I want to get to. One. So C1 is going to equal the one that we're starting out with. But after we have 1 more.
Yeah.
Okay. So my V1 is going to be unknown. That's what we're trying to figure out. Question. Okay. My C2 is going to be 0.5 over. And my V2 is going to be 50 milliliters. Now, I know that molarity is moles per liter, right? So I have options, right? One thing is that I have milliliters, so I should probably change those to liters. But if I pay attention to what I'm doing, right? My units are gonna cancel out when I solve for my volume, right? Because if I switch this around, I'll be able to solve for my V1. Is that true? Do my arbitrary manipulation. So, no, I got orange.
Oh.
I was colorblind.
No, I do.
Oh, that was, yeah, green and everything. So. And I solve for, because the one I don't know is my V1.
Yeah.
That's the one I want to get. Okay, so if I want to get to my V1, and I solve this equation for V1. Okay, so how would I go about it?
Divided by.
So I go C1, V1, C2, V2. I divide both sides by C1. Okay, that cancels this out, so then I get V1 equals C2, V2 over C1. You guys see that? So then I plug in my numbers because I have numbers, right? So my C2 is 0.5 molar. My V2 is 50 milliliters. My C1 is 1 molar. Molar is going to cancel out. And then I'm going to get what?
Five.
25 milliliters.
Yeah.
Okay, how many sig figs should I have?
2.
I should have, are you sure?
No.
So that's 1 sig fig, that's 1 sig fig. With division. How many sig figs should I have? I should have 1 sig fig. So my answer should be
You round up or not?
I don't know. Tell me, you round up or you round down?
In this
Think about
case,
this.
would it stay a 2?
It would stay at 2. That's right. So then my answer should be
At the 2.
sure.
2 milliliters of
You want to put money on that?
no.
Put your money on the table. Put $20.
I give you $1.
Put $20.
I'll have some of those.
You got $10?
No, wait, maybe.
Okay, put $10.
$2.
See if they have
I'm gonna 5.
Okay, I got some good points. Hold on.
I'll put
Let's
5.
see. You got a 5?
Take IOU.
Anybody got a quarter?
I do in my truck.
No, I don't want money from you. Who got 2 quarters? You got 50 cents. You got 50 cents? Okay, excellent. I like people who carry money to school. Thank you. 50 cents, perfect. Huh? No, just 50 cents, that's all I need. Because he's got $5, right? So he just told me that 20 and 2 are the same.
Oh, I see. You had a point right there. You had a point.
Oh, I have a point. What is the point? Are 20 and 2 the same?
No, don't be stupid.
Oh, no, it's too late now because you just told me that, right? No, just hold on. Just hold on to it. Somebody gives you $5. Never say you don't want it. You earned that money. Because you thought about it, right? Okay, so are 20 and 2 the same?
No,
Are 5 and 50 cents the same?
no, obviously not.
They're not the same, right? He's like, he learned the hard way. They're not the same. Okay, so since they're not the same, you guys need to understand that zeros, those zeros are placeholders. They are not the same amount. 25 is much closer to 20 than 2, right?
Yeah.
Okay, you learned the lesson?
Yes.
Okay, so you want your money back?
I hope so.
So I'll give you her money back. Thank you. Okay, so if we're talking about those sig figs, we have to remember the placeholders. Placeholders make up that money, right? So they make up to make sure that they are. Because it's kind of like me. If I owed you $2,000 for working this month, right? And I paid you $2, right? They both are one sig fig, right? But $2 and $2,000 are not the same, are they not? No, they're not. He's got to learn the hard way, right? Would you ever forget that lesson?
No.
Okay, because if you do, I'm taking this $5 back. All right. Okay, so we want to make sure that we use those zeros as placeholders. Okay, so then my answer is going to be
20.
20. That's right. Because this is exactly 5, right? We can't round it up. So it's 20 mils. If I'm using sig figs. Okay, how are you guys doing?
Pretty good.
We're supposed to use lyrics.
For liters, yes. So, but we got away with doing it, right? So the reason why is because those units cancel out. Normally we use liters, so we have to convert it to liters. But in this case, we could end up accepting milliliters, right? If they ask for milliliters. If they could ask us for liters, then we'd actually have to do the conversion, right? Because the molarities are canceling each other out. So then all we're going to be left with are the units of that volume, right? Which is in milliliters. So we can cheat in a way, right? So does that make sense? If the units didn't cancel out, then we would have to make that conversion, right? Because molarity over molarity, that's units, right? If they cancel each other out, then we'd be left with just milliliters. Okay. Okay, so that's going to be your intro for your calculations. What I'd like you guys to do is do the ones you can do, right? And then we'll try to do a couple of them together. And I'd like you guys to work in a group, your table groups. You guys make sort of butterfly groups like here. This is your group. That's going to be your group. That's going to be your group. And Mauricio is going to skip from group to group to make sure you guys understand. Zero. That's okay, let's hit that extra time. Oh, no, that was just 20 point. Okay, that was recent. 20 point. Yeah. Formula unit is okay. So when we're working with ionic compounds, which we haven't really talked about yet, we sort of talked about versus covalently compounds. Right? Can we talk about sharing? Okay. So let me, and then I'll explain to you what formula unit is versus molecular unit. So I'm gonna erase this so you guys can have 15 minutes going on. Okay, you guys know what an ion is, right? Okay, so we have cations and anions, right? So what happens in real life, okay, we're talking about sodium. Sodium is in group 1, it's a group 1 metal. Now, sodium is going to want to be like a noble gas, right? And to be like a noble gas, you could either give up electrons or you take electrons. Okay, now sodium is group 1 and it wants to be like neon, right? So it's going to be like neon, it has to lose 1 electron. So if it loses 1 electron, what would be the charge on sodium? Positive. Very positive. Okay, now chlorine. Chlorine is very close to being a noble gas. It's 1 away. If it gains 1 electron, it's going to be like argon. So what is going to be the charge on chlorine? Okay. Okay, so we have sodium who's plus, and you have chlorine who's negative. Now, how many of you guys dated in high school? Anybody dated in high school? Nobody? None of you guys dated in high school. Okay, you guys are full of crap. I cannot believe how much bull crap you guys are telling me there. Okay, so let me. Okay, so let me tell you a story, and maybe this will help. Remember, John Bill's memories, right? So when you were in high school, you know, you came home and you told your mom, "Mommy, mommy, mommy, I met this great boy. He is just so nice.
No
I
way.
just love him. He's the best friend ever. Oh my God, mommy, I love him. I love him. I love him. I love him." Right? And your mom looks at you and says, "Oh, honey, who is it? Who is it? Oh, it's Johnny Johnson, right? It is Johnny Johnson." Your mom says, "Johnny Johnson? Johnson's from up the street? Hell no. You ain't dating that boy." Your mom's like that? Yeah. Well, my mom was like that too, right? So you weren't allowed to date him. What did you do? Tell me, be honest, what would you do? You dated, yeah, exactly. You did exactly what your mom told you not to do. You dated them, right? Because they were the bad boy, right? And you were like, "I can change him. He's bad, right? You're the good girl, right? Okay, I can change." See, they're all giggling. Look at this. I never dated anybody. But all these giggles come out now, right? Because you knew you could change them, right? You knew it, right? And then the thing is that that's nature. That is chemistry. Because what it is that opposites attract, right? A negative and a positive. They come together. Now the thing is that a negative and a positive have to balance each other out completely, right? They have to have a total net charge of 0. So if you look at sodium, sodium has 1 positive, chlorine has 1 negative. Oh, perfect couple, right? So we end up with NaCl. So this is called an ionic bond, because they're bonded together by their electrostatic forces, those opposite charges. Now what happens when one of them is greater than the other? Like, let me give you an example. So I went through a phase where I liked dating bad girls, right? And one of the bad girls was a crackhead, right? Have any of you guys ever dated a crackhead? Any desire to date a crackhead, right? We try to avoid those things, right? Because it's a hot mess, right? Okay, so in a context like that, right? I am positive and she was negative, but she was way negative, right? We're talking about like C4 minus, right? And I'm here, I'm just Na plus, right? So it's just me that has that plus. They're going to take 4 of me to balance her out. Now I can handle that, right? That's like 4 times me. So that's Na4C to balance that 1, right? Again, they have to balance each other out. If they don't balance each other out, the relationship don't work, right? And so that's what it boils down to, right? It didn't work between us because it was just me. I didn't have my 4 twins, quadruplets. We weren't quadruplets to sit there and handle that one girl, right? Because she was up all night long and, you know, pacing. I couldn't handle it, right? So it didn't work out because there wasn't that balance. So you need that balance. It has to balance out to 0. So that's an example of an ionic bond, okay? Now, covalent Covalent bonds happen between non-metals, right? It's sharing of electrons. Now, the reason why it happens between non-metals and versus metals and non-metals, because ionic bonds typically happen between metals and non-metals. It's all about take and give. Okay, so the way I like to look at it is, so let's say that you guys are thieves. I know you guys aren't thieves, but if you were thieves, you're gonna be good thieves, right? You're not gonna be dumb thieves, right? Okay, now think about this. Think about this. Really think about it. Now you saw this really badass bike. I mean, it was bad. It was like stripes on it and everything like that. You had a lightning bolt coming down the side. It was a badass bike, right? Now, your neighbor has one. And there's a guy all across, 4 towns away has one. Now, your very next door neighbor has one. Do you steal from your next door neighbor, or do you steal from the guy that's way, 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 way across town, 4 towns over?
Still both and selling.
Okay, so you gotta take one or the other. You can't have both, right? You gotta make a choice, right? And you're planning to ride. You're not planning to sit there and sell it out. You're planning to ride. You're selling it for yourself, not for somebody else. Okay, we have to put these restrictions on there, obviously. So, okay, so now which one are you gonna take from? Why? That's like, hell, if your neighbor sees his bike is missing and you're riding the exact same bike that's very signified with that lightning bolt on the side, you're definitely gonna get caught. There's no question about it, right? So you're not gonna steal from your neighbor. You're gonna borrow from your neighbor, right? You're gonna say, hey, bro, come on, man. I'm trying to get this girl, and your bike is bad. Come on, man. Let me borrow. She just lives at the time they store. I'll give you gas money. Let me borrow it, right? So you're gonna be more likely to share with your neighbor than to steal from them, right? You're not gonna take from them, right? And so the way I look at it is, if you look at the periodic table, you have non-metals on one side, you have metals on the other side. You're likely to take from the one that's far away. The ones that in your neighborhood, you want to share with, right? You don't want to sit there and take from them because they're going to come back and get you, right? You're going to turn you to the popo, right? Turn you into the popo, right? So those are ionic. Ionic bonds, covalent bonds are sharing, okay? So it's sharing of electrons. Ionic bonds are give and take. Covalent. Now, if we're sharing electrons, there's 2 ways of sharing. Okay, so sharing can be done 2 ways. Let me give you an example. I have sisters. I have 2 sisters. So during Christmas time, we were a poor family. We would get one really good gift, right? So like one year we got an Atari for the family, and so we would get underwear and socks for everything else, right? So t-shirts. So the Atari, the deal was that we had to share it. My mom says, you gotta share this. So I'm being smart, right? So my mom, during the holidays, my dad was on the boat. My mom would go to work and everything like that. So when my mom was at work, I had the Atari, right? An hour before my mom gets off of work, my responsibility was I had to cook. I had to make sure the house was picked up and everything like that. So I made my sister pick up everything. And I'm being honest. I'm telling you the truth. I made her pick up everything, and I go in there and start cooking, right? And then after they finished cleaning up, picking up, and everything like that, I let them play the video games. So when my mom came in, she sees my sister's playing the video games, right? So then I'm like, I'm spreading over the hot stove and everything like that. Oh, I just finished dinner, Mom, and stuff like that. And Mom said, oh, you're such a good son. Why don't you play the video game a little bit, right? Like, okay, Mom, sure, right? So we share, right? Did we not share? I met those requirements. My sisters got to play it for about an hour. I got to play it for about 10, right? That's fair, right? We share. Is it even sharing?
No.
No, but it's sharing, right? Okay, so there are 2 types of sharing. There's even sharing and there's uneven sharing. Okay, even sharing That's called non-polar. Uneven sharing. That's called polar. Okay, so polar means that I get it the majority of the time and you only get it for a little bit. Like me and my sisters, right? Worked out perfectly for me, right? Even sharing means that you get it for an hour, I get it for an hour. You get it for an hour, I get it for an hour. You get it for an hour, I get it for an hour. So this is what's happening with the electron. The electron is either being shared evenly between the two atoms, or one of them gets it the majority of the time and the other one only gets it a little bit of the time. It's still sharing, right? And they serve two different purposes, right? And it usually works out the same way. There's a hierarchy, right? The one that is the strongest in what we call electronegativity is going to get the electron the majority of the time, where the weaker one only gets it a little bit of the time. Okay, now if they're both equals, right? So if my sister was like closer to my age and as big as I was, although my sisters got bigger and they got stronger than me, they start pushing out windows and stuff like that. That was later on, but they were still a little bit, right? Little when we started with the Atari, right? So there's that hierarchy. I was stronger than them, so I could bully them, you know, and stuff like that. Yeah, right? But when they got older, I had to start learning how to share evenly, which was hard for me because I was like, I'm the only boy. So they would double team me and stuff. So I learned real quick that I had to share evenly when they got bigger and stronger. So like I said, I got pushed out a couple of windows. It's hard way. So even sharing, they get it part of the time, you know, 50-50, even, right? And then uneven, 90-10. You guys get that? Simple, not too hard. Okay. Okay. Okay, so what was my point? Oh,
Kevin had a question.
you had a question, Kevin?
Oh, that's when you started talking about it.
Oh, okay. What was your question, by the way? Yeah, I forgot.
It was the,
Oh, it's the question on the thing. Right?
yeah,
Formula unit. I knew there was something. Okay, so you need to distinguish between ionic and ionic bonds and what we call covalent bonds. Well, covalent bonded structures are called molecular, right? They're typically molecular because that sharing is even though they're all considered to be molecules, right? That's going to be the molecular form because it's covalently bonded. Ionic formula is called formula units. So it's because it's really what happens with, let's say, sodium chloride, is because since it's positive and negative, right? So literally what you do, you form lattices of positive and negative charges, positive and negative, positive and negative, positive and negative, positive and negative. You form this nice, beautiful lattice. And I'll show you guys that in lecture Thursday, Tuesday, Wednesday, whatever day, 2 days from now. Right? Okay, so when we're talking about formula units, it's when we're talking about ionic compounds. When we're talking about molecular formula, that's usually what we're talking about. Now, to be honest, only a really strict chemist can care about it because you calculate the units both ways, right? Because it's sodium chloride, it's one sodium, one chloride, right? So you're going to calculate the same way, but a chemist cares about that name more so than anybody else because he's really concerned whether it's an ionic compound or whether it is a covalent. Does that help? So in other words, long story short, to get you right back, the formula unit is just calculating the atomic mass or the molar mass, but instead of using molar mass, you're using A and B, atomic mass. Okay. And it's done exactly the same. Okay. So working groups, see if you guys can help each other out, and then Mauricio and I will walk around, we'll make our rounds. See how you guys are doing. And we will do this until 4:30, and then I'll let you guys out. Okay, and we'll pick it up on
Wednesday.
that other day. I'm like,
Wednesday.
what is the day?
Next one.
Yes.
Wednesday.
Calculate the mass.
I can change it. Or,
Oh, I see.
Yeah.
One more.
Those are extras.
Yes. Oh, 8.6.
Don't know how to do this? Absolutely not.
Well, that's right here. Right? It says, first off, it starts off with one. That one. Everything else is good. So actually, do you mind if we do the first one together, or did y'all?
Yeah.
Everybody?
Yes,
Want to do the
yes.
first one together? Okay.
Yeah, give us this. Good.
Let's start. Okay, but you guys, we're doing it together. That doesn't mean that I do it. It says we do it.
Yeah.
Okay, yes, sharing is caring.
Yeah, we're really learning things, from all these.
Okay, so tell me, Ron was telling me. Yeah, help me out here. Sorry. So what is our given?
One atom of magnesium.
Okay, so we have one atom of magnesium, 1.00 atoms of magnesium. Okay, and they want us to calculate what? What do you want to get to? We want to get to the mass. Okay, so we want its mass. So mass is in what unit? Grams. Okay. So what do I know? What are some of the things that we can look at? So we have on our periodic table, that's going to give us what?
It's mass.
It's molar mass. So what are the units for molar mass?
34.3 to what?
24.
Point
24.305. And what are the units?
so.
What are the units? No, that's not the unit.
Oh,
Grams per mole.
Grams
yes,
per mole.
okay, sorry.
Grams per mole. Okay, so that's grams per mole, but this is atoms. So what do I know about atoms? Is there a conversion for atoms that we know?
1 mole equals 6.022 times 10 to the power of 23.
And that would be
1,
atoms, right?
yeah.
Okay, because we know that 1 mole can be anything that we want, right? So we want this to be atoms. So I have atoms. If I want to get rid of atoms, what am I going to use? Okay, 6.02 times 10 to the 23 atoms. So the atoms are going to cancel out. And then I have 1 mole. Right? So, and if I want to get rid of moles, and I want grams, then what else do I need? The molar mass, which we have right here. So we know 1 grams on top. And then we're going to put 1 mole at the bottom. Okay, and then that's going to equal, it's going to be all the heck this and thing.
36 bits will be
4.04 times 10 to the negative -20. And then that would be grams. Okay, so does that help? Okay, so another way of looking at it is you want to figure out your different conversions to get you where you want to be, right? So we started off with atoms. We know we have to get rid of atoms because we want to get to mass. So we go from atoms, so we use Avogadro's number. Give me my number of atoms, and then that gives me my number of moles, right? So then I need to get rid of moles, so I'm going to use the molar mass to get the mass. Okay, so what about the next one? How would we set that one up?
Times 10 to the
80 times 10 to the 22nd power atoms.
to get rid of atoms, we would yeah.
Avogadro's number?
Yeah.
So we're going to put Avogadro's number at the bottom. So we have 6.022 times 10 to the third. Mole. And what do we want? We want moles, right? Okay. So then atoms. That's a sulfur, right?
Yes.
So it would be 3. Zero point 046. After that, that would be remember, these are replacements, right?
465 since it's a 9.
Is that 4, 6?
Yeah, that's what I got to.
So 4, 6, 5. That's correct. You have to look at that.
I did it right.
No,
You don't divide by 100?
no. Where are you dividing it by 100? And then also here. Oh, I see what you're saying. Because you're dividing it by 10. Because you're getting rid of it. Does that one? So you divide it
I'll divide by 10.
10.
Okay.
Because the difference between this 10 to the 22nd, 10 to the 23rd is 1. Okay. Does that help? That should help you set up the next, at least the next one, if not the next 4. Get one laugh. Well, proud. Okay, Go team, go. Let's go. Oh, thank you. Danke. Thanks.
Oh. I got that. But- So we used to do it like that. Yeah, so they wouldn't. So just swap this down here.
They got that?
Yeah. Molar square. Okay, so we did is add them together.
Yeah.
Audit, I can't remember.
I have no idea what it is. That's one of them.
There's no formula.
Was that? Yes.
Mira, mira, pa.
You know he wants that answer.
After working with so many Mexicans, it's not even it's not even like embarrassing, but just because you said that, it's embarrassing.
Yes. So if they want to form the mass,
No.
everyone has would be just- it would be the mass trying to find the so the formula is-
I was used to it, but just because you said that, it's embarrassing.
So you gotta multiply that.
What is it asking? What is it asking?
Formula, let's see.
Yeah, you turn right too.
Exactly that, bro.
So this would actually calculate how many formula units, how many sodium chloride units that you have. So you're gonna be multiplying that out.
How did you get that?
So which question is that?
Plug it back into the calculator.
Okay, so for number 3, it's asking us for formula units, not formula mass, right? So in that case, since we're talking about formula units, they want to know how many sodium chloride units that you have. So that's going to be your quantity. So you're going to be multiplying that by Avogadro's number. Okay. Does that make sense? So if they wanted the formula mass, right? Then that would be the mass of the ionic compound. But they're talking about formula units. How many formula units do you have, right? So they're saying how many sodium chloride units, so individual sodium chloride units that you have. Okay, so let me see if I can explain it in another way. Let me see if I can find the image, because the best
So
thing,
how do you plug it in?
because you guys always give them that look. Okay, I know.
Because that makes a big difference.
The other way around, so you get this first, right? You don't get that number, and then you get this number, you divide it whatever you got from that number, because there's no parentheses.
No, I found some other stuff, but hold on. Okay, so this one, so 2.80 divided by 6.022 times 10, but this number is going to be in parentheses. So that you, because you don't want it to be following PEMDAS. Yeah. Because if not, it's going to go by PEMDAS. It's going to be some more stuff. No, you divide.
You divide this.
Thank you. Question does that.
I don't know.
Yeah, we wanted.
I'm used to it. But just because you said that, it wasn't expecting it. Okay, but
All right,
So
so
you
write
get some?
something down. Write something down. Formula units equals number of, what is it? Sodium chloride. You guys want to join us? Is that right?
Yes, please.
Okay, so let me show you what I mean by formula units.
we round it, or just the best way to 2.9.
Okay, so this is really what sodium chloride looks like, because it's a combination of plus minus charges, plus minus charges, plus minus charges, right? But if we look at this, right? Here's our sodium, here's a chloride, here's a sodium, here's a chloride, here's a sodium, here's a chloride, so formula units would be how many groups of sodium and chlorides do you have, right? So that would be one formula unit. This would be another formula unit. This would be another formula unit. That would be another formula unit. So you're calculating how many of those that you have all together. So that's the reason why you're multiplying it by Avogadro's number, because you're doing a formula units of those.
So it is a translation between two quantities.
So what do you mean by two quantities? Because it depends on, like, so for instance, sodium chloride, so that's 1 plus, 1 minus, they're evenly matched, right? If it was magnesium chloride, magnesium is a 2 plus, so we need 2 chlorides. So then that would be for every 1 magnesium, you'd have 2 chlorides, or, you know, so does that make sense? So when we're talking about that formula unit, it's the sodium chloride, that's 1 formula unit. So you're trying to figure out how many sodium chlorides you have all together. Right? Does that make sense?
So molarity refers to how much total you have.
That's right. But now you're just telling me what,
Translating it
yeah,
into-
to actual quantity, right? So you're saying this is how many formula units, how many sodium chloride pairs you have.
Okay.
Okay, does that make sense? So a mole is just everything, like I have a box that's a dozen of donuts, right? So that's 1 dozen, right? How many donuts are we having in there, right? But let's say everybody eats 2 donuts, right? They have, or donuts that are connected together, right? That are matching each other.
I don't need that.
What's your thinking?
That plus that.
Remember, formula units, this number. This chloride, sodium. Sodium chloride molecules you have. And that number. Trying to figure out how many number of sodium chloride molecules you have. In that 1.088 moles. So instead of, I can see how you're trying to approach it. You're trying to add all this up and trying to get the actual mass, but since you have the moles, this would just be simpler to translate it by 1 step into the number of molecules you have. So how many atoms or molecules are in a mole?
Or you could say, sodium chloride.
Sure, so that's more.
How would you approach it? Sure. Looking at the number of sodium chloride molecules in this.
Conversion. Conversion. This is no formula, is it? Math, there's always a formula.
You go about it.
This is what's confusing. There's no set formula.
Yes.
Chemistry.
That's why I'm not taking chemistry.
Reality check you are.
Not imaginary.
That would be your approach.
Yeah, that's the part.
Got it. He said, "Put that in with the lead."
Yeah, that's the first step.
So remember, you multiply by the top, divide by the bottom.
Right?
Wait, so I did the opposite, is what you're telling me.
Yeah,
Put
because
this up
doesn't
here.
it all have to be on the bottom?
Yeah,
I'm not even gonna correct you guys over, right?
Right?
I wanna watch you guys step by step.
Right.
You're like, you could teach me on my paper.
Remember, look at the structure. You have the right
Remember,
numbers, but just the where they're placed.
This means 1 mole, right?
One more. So that
Remember how you want it to cancel out?
it's 60, but then there's 2.
Oh, we got it.
That's O2. Oxygen is always O2.
So you multiply 60.
Okay, that-
60 times 2, that's right. And then that would be grams per mole, right? That's why you guys are supposed to work in a group. You guys are always individuals. You don't have to group work, does not work. So,
Well, I'm not gonna do this by hand.
You have the right numbers, remember? So what's the 6.2? Yeah. Don't overthink it.
Grams per mole, right?
How are you doing?
Because it has a molecule, right? So, you know, the oxygen.
So we just set up right for the okay. So remember parentheses to that or what's the. And then you already know how to do number.
Oh, yeah.
You know what?
We just talked about it. You even mentioned it. You told me which ones are Ionic compounds? Is it okay? It's oxygen. Okay, so there's talking about oxygen. Yeah.
Remember how you don't count the ones that are given that are set in stone, remember? You know how 6.02
Okay, so
times
you're
10
starting
to the
right
23rd
there.
energy. But this one's a given, and that's concurrence to the problem you have. Right? So that's where you're gonna take.
Okay, so now how do you get rid of molecules?
And you know why there's 3 6 fixing? You know why there's 3 6 fixing and not 2? That's actually the decimal and that the zero count.
Okay, so
I got
yes,
one answer.
this time.
Maybe.
Because this here.
And if there wasn't a zero, it's still a molecule.
No, it would be, so it'd be another one.
So we're gonna do
Because
molecules.
that's not, that's a trillion. Get in that proper term. But you're sure, you're so sure it's a zero that you said it. No, otherwise you would have left the blank. There wouldn't be. You remember why you rounded, right? So just- Any questions?
Yeah. That table, exactly. And then.
Excuse me, Mr.
Think of an approach.
I don't know what you're laughing at, Mr. Teacher.
Yes.
I got this. Is this the correct answer or am I
Yes.
bullshit up?
I'm not even calculating our trust. You put it over, you put parentheses, right?
Yeah.
Parentheses around this.
I didn't.
You did?
I didn't.
You're right. Don't forget 6 fix.
5.3.
I just really remember.
So the molecules will get watched. So yes, molecules.
You were laughing at me. Okay.
And then what's it? One more.
5.3 times 10 to the 26.
Okay, so what's your?
What did you do?
I have a question on mole.
So why is it 10 to the 27?
Oh, I think so.
Okay, but there's two from every.
But why is it the 27?
Two oxygen.
Even know how big 6.022 times 10 to the 33rd.
Yeah, but like,
Yes, so much easier.
You think a power of 10 is pretty shit.
yeah, I'm just saying. So did I get it right?
Hey, as long as your setup's right and your numbers are
Okay, how many of
correct.
you guys got to 4? Is that good? You got to 4?
I'm on number 4.
Number 4? Okay, I'll let you guys work it out a little bit.
Don't know what to do.
What you give it?
So what do you would you like for the chloride? Is there an unknown that you want to get?
We're just gonna use the iron. Because they get, it's gonna be one of the two, right? So, iron, that's what.
Oh.
Iron 3.
Yes, yes, I remember. I said nothing about iron here, but
Oh,
yeah.
Okay.
So number 4. Let's see if we get number 4 yet.
I got it.
Got it?
I got it set up.
Or whatever, right? Or the formula
Number
unit.
4.
Right? From there. So,
Okay, what is my given?
oxygen goes to the
What is
bottom,
given
right?
to me?
A mass of
what are you gonna convert it to? What's your first?
1.04 times
You're
10
gonna try to find the mass. That's a given. That's oxygen. Oxygen
Okay.
right here.
1.04.
So do you already know the mass of 1.04 times 10 to the 23rd molecules of oxygen?
No, that's why I'm asking.
Right?
So
Now, it says of oxygen, we
What
know
number
when
of
we
moles?
talk about oxygen by itself, we're talking about O2.
Yeah.
Because we know that O2, oxygen, is diatomic. So it always exists, but it's all by itself as O2. Okay, and that's also part of the reason why they say molecules, double. Right? So, because otherwise we would say atoms. So we know that Avogadro's number,
That's good.
it
Don't
doesn't
forget
have to
six.
be atoms. It could be shoes, it could be underwear, it could be pantyhose, it could be boyfriends, it could be girlfriends, it could be donuts, right? We know that 1 mole of anything is going to be 6.022 times 10 to the 23rd. So I can use molecules, can I not? Yes. Okay. So I can equip molecules.
Oh, I didn't have.
Okay, so then, what do you think I'm going to do with it? Where? Top or bottom? Bottom. So I'm gonna put 6.022 times 10 to the 23rd molecules of oxygen. So then my molecules of oxygen. Yeah. And then we know that that's going to equal 1 mole, right? Okay, so then what am I going to do? Because what am I looking for?
Molar mass.
I'm going to use my molar mass, right? So what is the molar mass of O2? 32. There we go, it's 32, 16 times 2, that's right. So we know that it's going to be 32 grams for 1 mole of O2. So then moles cancel out. Oh, you guys can't see it. When I do that, you should just throw something at me. Say, Dr. Henry, tell me. I'm looking at the screen, there's these red and blue, or red and gray dots everywhere. That's not right. Okay. So who's doing the heavy lifting? All right, that's about equals. What is it, Mom?
Yeah.
504.
But a procedure.
5.504. Right. It should be 5.50.
Oh, I see. I got
Spread it out with 3 safe fix.
Yeah, I see. Hey, I got the same one.
Yeah, 5.0.
5.52646.
Okay, so the flash. Okay, so then if it was 2 here, then what would be the numbers on this? 2, 6.
Yeah.
Okay, so then we look at the 6. On which side are we going to round up? We're going to
We're
we're going to round up, so it's going to be 5.5. 32. So this is from the periodic table, and it's a rounded anyway. So periodic table we don't use to determine our state. We're only going to use what we studied out. All right, so that's it. Okay, how was it?
What for me, I started putting what goes on top, what goes on bottom. I always mess that up.
Think about what you want to get rid of, right?
Yeah.
So the way I always remember it is that it's like, where do I want to go, right? It's kind of like dating, right? You put the one that you want on top, they're the priority.
Yeah.
So they always go on top. The one that you're trying to get rid of, right? They're in the bottom because you don't care. Right? Okay, so we'll pick this back up on Wednesday. So I'm kicking you guys out. I love you guys. Yes.